Have you ever stopped to think about how an idea in your head, just a concept, actually becomes a working app on your phone? Well, the magic in the middle, the thing that makes it all possible, is called a programming language. And over the next few minutes, we are going to completely demystify what that means and how it all works.
So let's start with a big question. What even is a programming language? At its heart, you can just think of it as a bridge. It's this special, structured language that lets us humans communicate instructions to a computer, translating our ideas into actions that the machine can actually understand and perform.
All right, here's what we're going to unpack. We'll get into why we don't just talk to computers in ones and zeros, explore the huge difference between high-level and low-level code, understand the grammar that holds it all together, see how our code gets translated, and finally, figure out why on earth there are so many different languages out there. Let's do it.
So, first things first, let's tackle the most fundamental question of all. Why do we even need programming languages in the first place? Well, the short answer is they're the only bridge we have to get our ideas across to the machine. And that's a totally fair question, right? I mean, computers have their own native language. It's called binary. So why can't we just, learn to speak it?
Well, because it would look exactly like this. And honestly, just imagine trying to write a simple email app using only that. Or worse, trying to find a single typo in that wall of numbers. It is just not how our brains are wired. We needed a much better way.
And that really gets to the core of the problem. We think in words, symbols, and complex logic. Computers, on the other hand, only think in terms of on or off electrical signals, those ones and zeros. That massive communication gap is exactly what programming languages are designed to solve. They are our essential translators.
Okay, but here's the thing. Not all of these language bridges are built the same way. And that brings us to a really important concept, the difference between high-level languages and low-level languages. And you can see the difference so clearly right here. On one side, you have a high-level language like Python. The command print hello world is super readable, right? It's pretty close to plain English. But then you look at a low-level language like assembly. That command, move AX5, is much, much closer to what the hardware actually understands. It's a direct instruction to move the number 5 into a specific tiny storage spot on the processor. So, why would you ever pick one over the other? Well, it's all about trade-offs. High-level languages are way easier for us to write in, which means we can build things faster, and the code can usually run on all kinds of different computers. But with low-level languages, you get raw, blistering speed and a ton of direct control over the hardware, which is absolutely essential for things like game engines or the core of an operating system.
Now, every language we speak has rules, right? You can't just throw words together. Same thing goes for programming. And in the coding world, we call these rules syntax. It's basically the grammar of code.
Yep, syntax is just the formal set of rules that tells you how to structure your commands so the computer can understand them. If you get it wrong, the program just won't work. It's kind of like in English. We say, he is playing, not playing he is. You gotta follow the grammar. And every single programming language has its own unique set of grammatical rules.
And here's what's so fascinating. Check out how two different languages can express the exact same idea using totally different syntax. Python here uses a colon and a simple indent to group the next command. C++, on the other hand, uses parentheses, curly braces, and a semicolon. The underlying logic is identical. If x is bigger than 10, print the word greater. But the rules, the grammar, are completely different.
Okay, so we've written our code, we've followed all the syntax rules, but the computer still only gets that ones and zeros machine code. So how do we get from our human-readable code to the machine's language? That final translation step is handled by one of two things, compilers or interpreters.
So first up, let's talk about the compiler. I want you to think of a compiler like a book translator. They take your entire program, the whole book, read it from start to finish, and translate the whole thing all at once into a brand new, standalone file. On Windows, that's often a .exe file. Only after that whole translation is done can you actually run the program. But because it's already in the computer's native language, it runs incredibly fast.
An interpreter, on the other hand, works completely differently. Think of it more like a live translator at the UN. It doesn't translate the whole thing beforehand. Instead, it reads your code one line at a time, translates just that line into machine instructions, and has the computer execute it immediately. Then it moves on to the next line. There's no separate file created, it's all happening live, which makes it awesome for quick tests and learning. And then you have some clever hybrids, like Java, that kind of do both. It's a two-step process. First, the Java code is compiled, but not into machine code. It's compiled into this intermediate thing called bytecode. You can think of it as a universal blueprint. Then, a special program called the Java Virtual Machine, or JVM, acts as an on-the-spot interpreter for that bytecode. This is the secret sauce behind Java's famous motto, write once, run anywhere. As long as the device has a JVM, it can understand that universal blueprint.
So let's recap. We have high-level and low-level languages. We have compilers and interpreters. All of these variations lead us to one final big question. Why are there so many languages? And the answer is actually pretty simple. It's all about using the right tool for the right job.
And you can see how this all shakes out in the real world. If you need the absolute blazing speed for a video game engine, you're going to reach for a low-level compiled language like C++. If you're doing data science and need something that's easy to get started with, a high-level interpreted language like Python is perfect. And for making websites interactive, there's really only one game in town, and that's JavaScript. Every language has its own sweet spot.
So, if you take one thing away from all of this, let it be this. There is no single best programming language. The next time you hear people arguing about it, you'll know the real answer. There is only the best language for the specific job you are trying to get done.